I want to talk about object allocation in .NET, specifically around generic types or unknown types to you. And this is in cases of plugins. This is if you have generic factory systems that you don't know what the type is up front, right? Obviously, if you're just doing, var or object O equals new object, this is as fast as you're ever going to be able to get for newing up, for initializing or allocating a new object, calling its constructor, right? It's not going to get any faster than this. There's no trick that makes this any faster. There are some tricks we'll talk about related to this later, but if we have to allocate, if we have to create a new object, this is the fastest way to make this happen, right? But what happens if we don't know what object is, right? We have a static void create that takes in, it can take in anything we want, type, right? Assume this is some type of weird factory, maybe taking a string, maybe taking an enum, maybe you're reading a type from file because you're using some type of inversion of control or dependency injection. There's all types of reasons, or you're using a plugin system. There's all types of reasons why you might not know exactly or have a function that you need to new up an object and you don't know the type explicitly, right? Or you might see a lot of code like this in inversion of control situations, right, where they have a generic, which takes in a type, right? So now T, we can pass in T for a type. And there's different ways you can new up this T, right? We could just say return new of T, as long as we give this where T new, right? Sorry, hold on. Email people bugging me too much. Sorry, okay. So now we should be able to return a new T. This is a void, let's make that T, right? And this will be correct. Let's take a few little tries here. Oops. We can also have static object create return new object, right? Right. Let's see. Create native. We'll call it that, right? We have to give this different names, otherwise it doesn't really know what it's doing. And then we should be fine, as long as we do this correctly. So now we have two functions. We have a create, which takes in a generic creator, which you can pass a type, right? So we can go var o equals new. Oh, sorry, not new. Create native, or we can do o equals create of object, right? Everybody understands generics. Now, syntax-wise, operational-wise, these are exactly the same functions. We're going to new up an object. We're going to new up a type, which we're going to pass in as a generic of an object. Let me switch back to chat here for a second. And we're going to try and take things kind of slow today, guys. We're going to take things kind of slow. So hopefully you're along for the slow ride, because I want to make sure people understand what we're talking about. And I'm going to switch back to chat. Not that. I'm going to switch back to chat. Who out here, what do you guys think is going to happen? We have a native, right? We have just new object. Here, this is exactly the same. It's a generic type. What do you think is going to happen? Do you think we're going to have the exact same object allocation time? Is a new of a generic type and a new of an explicit type? Is this going to be the same opcodes? Is this going to be the same performance? Is this going to be faster, or is this going to be faster? Let's hear it in chat. I'm just curious. What do you guys think is a better approach to doing this? And Diego, why do you need inspect IL? We're going to get into that in a moment. Let's see what you guys think. Wise Coast, same speed. Cool. Okay. Same speed. Different opcodes. Of course, it's going to be different opcodes, more than likely, right? But same speed. All right. Ramses thinks the generic's going to be slower. You have no strong feelings one way or the other, James? I love it. CaliQ, what does this do? This explicitly lets us know that you can new up T, right? If I take this off, while normally this will not work, right? Sorry, let me take this completely off. We don't know that T is a newable type, because T could be a struct, T could be a value type. We don't know what it is, so this would not compile. We have to give it a hint. We got to give it a constraint on the generic that says T, only types of T that implement new can be used. Lady Subu, I'm going to be here all day, man. You know it. Alright, so Cornflower thinks they're going to compile to the exact same thing on release mode. Alright, the compiler's optimizing. Well, let's do this, guys. Let's take a look at a release mode IL. We can look at the IL, right? We don't have to guess. We can go look exactly what the heck's going on here. Alright, let's go look, guys. I love it. Everyone's got their opinions. I love hearing that, guys. We just built this. Let's run it. Make sure it doesn't crash. Obviously, we have proper code, right? And then let's go look at ILDASM. Let's go see what the heck is going on here. So we have two create methods, guys. We have two create methods, right? We have a create native, and if we look at the IL for this, this should look exactly how I would expect it to look. All we're doing is a new object of type object, and this is the constructor that the new object operator should use, right? The default constructor. And new object will put that new object instance onto the stack, and now we're going to return. And since we're returning and there is an object, there's an item on the stack, so we're going to return that item, right? So create a new object, return this new object. Two IL lines, right? Two opcodes. Two opcodes. All right, here we go, guys. Here is our generic create. Here's our generic create. Whole bunch of IO going on now, right? Oh my god, there's even some boxing going on. No good, no good, no good. So this has two locals that it has to initialize, and these are for tokens, because T is a token, and that's just how generics work in IL, which is fine. We have to initialize the object. We have to then load it onto the stack. We have to box this freaking thing. We have to then do a check. And why are we doing this? Because we don't know what T is. We don't know if T is a struct. We don't know if T is an object, right? We don't know if it's from a value type or from a struct, basically, or from a reference type, because it could be either. It could be either. So it then has to load all this up just to do a check, to say, hey, are we an object type or are we a value type? If this is false, we're going to go all the way to 1A, which is say, okay, let me new this up, and we'll talk about this in a second. Let's go and new this bad boy up. Otherwise, we just call a init object on it, because that's how you create structs. It's an init object call, not a new object call, and then we're going to return it, right? So that's fine. However, if it is an object call, why aren't we calling new object? Why aren't we calling new object? Well, we can't call new object. We don't know what T is, right? We don't know what T is. Instead, what it's going to do is use the activator.create instance, which is a reflective API call that says create an instance of a type. And when this is the tokenized version of the type of what we're trying to use, right? So that's what this comes from. So that's what it is. We're going to get a create instance, and then we're going to return that. But still, looking at this IL code, we don't know if it's going to be slower or faster, right? We don't know what's going to still be faster. Now, obviously, this is more IL code, so we could probably guess, and this is release mode, by the way. This is not debug mode. We could probably guess that this is going to be slower. How much slower is it going to be, though? Because that's what matters, right? So just looking at IL doesn't tell us that, is this going to be 5 times slower? Is it going to be 2 times slower? Is it going to be 0.5% slower? Because if it's just that much slower, we don't care, right? If it's that much slower, it's not that big a deal, So what we need to do is go write some measurement code for ourselves. so that we can do that. So I'm just going to copy and paste a little code in here that I wrote earlier, only because, I'm lazy. Just a little lazy, but it's good for us. And we'll explain what I'm copying and pasting here, guys. Don't worry. Don't worry, because we're going to be using this all day today. So I just wrote a little measure function. It's a little test function for us. Let me get stopwatch in here. So what does this do? This takes in a string what. This is just for outputting so we know what we're measuring. How many repetitions should we measure our action? And then we're going to get averages, min, and max around that, right? We take in an action, which is basically just give me a anonymous function to run, right? So we're going to warm it up. Why do we warm it up? Well, because remember in .NET, we compile to IL. The first time you execute a function, the jitter is going to have to go and JIT that function and everything around it. So the first time you execute a function is always very slow when we're trying to do measures, right? So in .NET, when you're doing any type of measurement, make sure you always warm up your code. So we do a little warm up on it, just to make sure it gets JITted. And then this is very simple code, very simple measurement code, right? We're just going to go through our reps. We're going to use a stopwatch to measure how long each action takes. This is not super scientific, guys, but it's good enough for what we want to do. So once we have all of this data into a double array, right, we can then use some link stuff that gives us min and max and average and all that fun business, because that's all we care about. We just want to measure how long each action takes in our repetitions, and then we can get averaging out, right? So we have a measurement function. We've gone and written these two functions, so why don't we just go measure these and see what's going on, right? So reps 5, let's see, how many iterations do we want to do, right? So reputations, and I'll show you why we do iterations as well. It is, we'll say 10,000. Let's do 100,000 iterations. For something like this, we want to stress it out so we can actually extract out some needful data, right? And then we can call our measure function now. This is create native. No problem. Reps. And we're going to create a lambda, just a little anonymous function, to do what we want. And for here, for int I equals 0, I less than iterations, plus I. We want to stress out create native, right? That's all we want to do, and this will measure our native function. Now we can come in here and we can do a create of object. And we can measure this as well, right? Give me a moment. Oops. Okay, let me get my chat back up. We can see what's going on. Here we go, guys. Let's see what we're doing. So, let me change our name. Create generic. What is our crazy differences here? So, on average, this is every call, by the way, and this is in milliseconds. On average, our native create function is 0.4 milliseconds. On average, our create generic is 12 milliseconds, guys. Now, I know we're looking at this and we're saying 12 milliseconds, that's nothing. 12 milliseconds is actually not nothing, depending on your use case. Now, obviously, if you don't create a lot of objects or you don't create a lot of dynamic objects at runtime, if you don't know, again, this is about not knowing the type at compile time, right? Sometimes you don't know the type at compile time for various reasons. Maybe we have a scripting system that dynamically can create objects and we don't know what that object type is off the key, right? So there's a lot of reasons why we might need to create objects generically. And that's a pretty big difference. Pretty big difference. Ubi. Same operations with the same number. The compiler checks that actually don't execute. Nope. Nope, not at all, Ubi, not at all. C# does not check that. So, right, guys. Now, remember, .NET, for newing up objects, we have to be a little careful. Garbage collection is kind of kicking in on us here as well every once in a while. And if to prove this out, say, all right, maybe this is a garbage collection problem. We could fix this. Let's go make sure our test is still correct, right? And if we do our generic first, we do native second, we still have a huge problem. To be doubly sure, we're going to go and run a collect. We're going to do a GC wait for pending finalizers and collect again. Do a full collection process here. We'll move generic. Do this. Oops. Give me a second here, guys. So we'll try and take out the garbage collection noise, right? Because there could be a little noise coming from the garbage collection between these test runs. Let's run that again. Let's see what the heck's going on. We still can see that there's a pretty major problem, right? 10 milliseconds versus half a millisecond. Pretty damn huge, guys. Pretty damn huge. And here's the thing. This type of code is not uncommon. This type of code is not uncommon, right? If you look at frameworks all over the place, you will see this type of usage all over the place, guys. All freaking over the place. Now, I'm not done. There's other ways we could go about doing this. This works. This only works in a generic sense if we know the type, again, if we know the type at compile time, right? We still need to know what the type is at compile time, and we want to generically create it. Because since this is a generic. There's another create possibility where we pass back object. We'll take in a create. We'll call this create reflect, which passes in a type. Right. So there's also create scenarios where we have the native. This one's fine. We understand this. This is a scenario where you're going to pass in a generic. You're going to pass in the type as a generic, which means it's in at compile time somewhere. You know what that type is. Otherwise, you can't call that generic like that, right? There's another scenario, and this is more of a inversion of control dependency injection type system. Say you have a config file, and in the config file, you want to dynamically set which object type it should use at load time. We do this in video games a lot for data-driven operations. Or in a scripting language, you don't know what the type is, right? You need to reflect, you need to inflect the type. Sometimes you might pass in a string. You might pass in a string or an enum, all right? Enum object type, whatever that enum might be. And then from that enumerator, you do a switch case through it. Say, here's this object type. There's lots of ways you could do this, but sometimes we need to go full-on reflection, and we don't know at the generic time what the type is. We need to be able to pass in a type or pass in a string that can look up the type reflectively for us. But let's assume we just have a type, right? There is a .NET gives us a mechanism to create a new instance based off of a type. And we kind of saw that in the IL, right? We saw that in the IL in our code, which makes things a little easier. Which is fine. This is going to return using the activator create instance. My brain's not working yet today. And this is where you can pass in type, right? So then we can just return that type, right? Oops. So now this is the reflective way. This is how you use reflection. And ultimately, by the way, this is using the same thing here. It's just looking up the type for us. This is just some syntax sugar basically around this for us, right? But here is us directly calling and say, all right, well, if I just pass in the type directly and I use an activator create instance on it, this is doing the same thing. Let's go see what the performance looks like when we use this. All right, so we have create generic. We have a little test case here. Let's do this again. Create. I can't spell create today, apparently. Reflective. And then this is just going to create. Reflect. Let's see what happens before we get to our issue, right? Oh, and to take out the type lookup, cost, because we don't care about that in our test here, right? We'll say type object type is equal to type of object, right? So we'll pass that in. We don't want to do this type of lookup. This is pretty fast. It's not that big of a deal, but we don't want that muddling up our test results. Let's see what we get here, guys. Let's see what we get here. Well, what do you know? What do you know? While we're at about 10 milliseconds on average for generic, reflect is a little faster, guys. Reflect is a little faster than our original code. Did anyone expect this? Did anybody expect this? That our reflective object create would be faster than using our generic? Did anybody see this happening? Did I blow some minds? I don't think I blew that many minds. And why is this going on, guys? Very simple reason. Let's go look at the IL again, right? Remember, always check your IL for performance stuff like this. Let's go back. Let's take a look at what create reflect does. Create reflect, very simple IL that we're loading our arg, which is the first argument into the function, which is a type. Then we're just calling activator create instance for that type and returning it, right? Three ops, that's it. Let's go back. Let's take a look at what our generic create does. Our generic recreate has to do a whole bunch of stuff, right? We got to check: is it a struct type? Is it a value type, or is it a reference type? And depending on what it is, ultimately though, it's coming back to that activator create instance for the type, right? So ultimately, it's calling back into here, but there's so much more boot up code to make that happen. And this comes down to, unfortunately, guys, unlike C++. Unlike templates in C++, templates in C++, the code generated in C++ for templates does not have any of this weird boot-up code around templates, around templated arguments, right? They bake in a whole new class around that type. C#, however, or .NET, when it uses generics, doesn't do that. It has to emit IL to kind of make some of this happen. And remember, guys, we're going to get slightly different results every time you run this because of garbage collection. So you make sure you have enough test stressing going on, getting enough averaging, run this a few times to see what you get. But on general, we can see about 10 milliseconds for generic. We shave off 3 milliseconds. We can shave off 3 milliseconds when we use reflect. And this is our baseline, right? Create native is our baseline. Still, though, guys, still, this is still not fast enough. We can get even faster, everybody. We're going to go faster and faster. And how the heck are we going to go faster? Well, my friends, I'm going to switch chat up because for a few minutes, we're going to go write some code, and I'll get chat back in here. But for the moment, let's switch away from chat. Let's talk about how can we go fix this problem. By the way, if this is even a problem you need to fix, right? This is not necessarily a performance issue in every C# application. This is a very specific optimization that we're talking about. And sometimes we get to those places where we need to do these type of specific optimizations. But not in every case is this a problem. Just so everyone is clear, right? How are we going to do this, guys? How are we going to do this? All right, so to make this happen, I'm going to go create a new class. And we're going to call this a fast object allocator. We're going to create a new class to make this happen. And I'll explain why we're wrapping this as a class and not just as a function somewhere. We want to make this a public static class. We're going to use generics here, by the way. Generics aren't bad. I know I just said, hey, be careful with generics, but generics aren't bad. Even though we're going to create a fast object allocator around that use case where we can pass in a generic type. By the way, you can also, what I'm going to write, you can also rewrite to take in a type instead of passing in the type as a generic, right? Instead of templating it, you could pass in a type and still make this work. It's just a little bit, the code probably is going to be a little different. And we will only want to do this on types where T is newable, just like you saw earlier. Oops. Okay, so we're going to create up a bunch of static data. to make this happen, right? So what am I going to do, guys? What are we going to do? Well, we looked at IL. We saw how IL works in our very optimized case. In our create native, it's just a new object with a default constructor, or the constructor that you want, and a return, right? It's two IL operations. Well, guess what, guys? Just like in C++, we could emit our own IL and bake it into our process at runtime and then use it. That's what we're going to go do, guys. We're going to go build our own newable delegate, and we'll see how fast that is, right? So this is what I talk about when we get to some really advanced C# stuff. Not very often do you see a lot of C# or a lot of .NET developers writing IL themselves, and especially not writing IL based around input parameters and specializing it, and we're going to get into that. So I just want to create a delegate, right? So this is just how I want to create a delegate type of a funct for a type, because this is, if you know what funct does, right, if we look at the IntelliSense, this is our result, right? Our return value is that type, because we're going to be creating a new object of that type. So I just want to create a function that returns T, call it M object creator, and we'll initialize it to null at first, right? Because it's static, I want it null. We're going to lazy load this, and I'll talk about what .NET does around static classes of generic templated types. Okay. Let's go write this little sucker. It's really not hard to write this, which is great. So we'll call this just new. We don't need to template it here, because since our class is templated, we can use T wherever we want, right? And we're going to return T, which is awesome. First thing we just want to do is check if this object creator is null. Because when I talk about we're going to lazy load this, this is what I mean by lazy load, right? We initialize it to null. We're going to create it. We will go and create this on the fly. Now, I could optimize this even further by creating a static constructor, and maybe we'll refactor this in a second. Using a static constructor, initializing mObject creator ahead of time, and we'll save this branch check, right? Because this is a conditional check that we're going to have to make every time we want a new. But let's do this first, and we'll see if we can then optimize it away. Maybe it'll get a little faster, right? So we just want to get the type is equal to, instead of using var, I know I get bad with using that sometimes, I'll spell out exactly what we're looking for. Object type is type of T. We need this. This is important. We need to know what the type is. But we're only doing this lookup once. Remember, we only do this lookup once because we're going to set object creator. Alright, so now I got to use a little bit of reflection, everybody. I got to use a little bit of reflection to go look up the default constructor. And you could rewrite this if you want. Say you don't want to just use default constructors. Maybe you want to use constructors that can take a parameter, or 2 parameters, 3 parameters. You can write this however you want. For now, for our test case here, for what I'm just trying to teach you guys, we're going to use default constructors or parameterless constructors, right? From our object type, I can get the constructor. This is reflective work here, and I want to say new type, built-in array, right? Just an empty array which says, hey, go give me your parameterless constructor, which is oftentimes the default constructor, right? And this returns a type of constructor info. And we'll call this our default CTOR, default constructor, right? We need to add in reflection, namespace. Excellent. All right, so now we have the type. We now have the default constructor. Let's go generate the IL. Let's go create a method and embed our IL. And how we do that, and this is very, very nice in .NET now, because we can create what we call dynamic methods. And dynamic methods can get destroyed. The old way of emitting IL in .NET, you would have to go build a dynamic assembly. It would have to get written to disk. It would get compiled to disk. It can then get loaded back into memory, and it stays in memory for the life of that app domain. But now in the world of new .NET, this has been in here for a long time now. We have dynamic methods, which is great, right? So dyna method for now is equal to a new dynamic method. And what does a dynamic method take in? We give it a dynamic method. Is not a class. Basically, a dynamic method, think of it as a static function, a static public function that's free floating. It gets baked into an internal assembly, an internal class, but we don't care about that kind of business, right? And let's add our constructors. We just need a few things. We need to give it a name. This is the class name. We don't want this to collide with anything else in the system since we're dynamically creating this stuff. I'm just going to bake in a way to make this generic, right? So we're just going to create a GUID, new GUID. So basically, we're going to get a function name of underscore GUID. Oops. I just want a function name of a GUID, right? So we're creating a random function name, but we don't care about the function name. We're going to have a delegate to use this. The function name is to make sure there's no clash. There's no namespace clash. The return type is our object type, right? So this is a method. This method has a return type, and it's type of t, right? So that's why we look up t. And then it has parameter types. In this case, it has none. If you want to rewrite this to support parameters, you would just have to pass in the types as a list, or as an array of the types. But that's fine. We don't care about that for now. So here we go. We have a dynamic method. All right, how can we go use this dynamic method? Well, that's what IL generators are for, guys. We can create an IL generator from our dynamic method. Get the IL generator, which now lets us emit IL. We can go and push in IL and create this dynamic method on the fly, right? So that's what the emit keyword is. And now we have a bunch of opcodes. And if you remember what it looked like, let's go take a look. 1 second at the IL disassembly of our create native, right? These are our two opcodes. We have a new object of a constructor, right? And then we have a return. Two opcodes, guys. That's all we gotta emit. That's pretty easy. We could do that. We could do new object opcode, and the parameter the argument that goes to that new opcode is our default constructor, right? Is our default constructor, and then IL emit. That's gonna it's gonna call new object of that default constructor. That's gonna go on the stack. All we have to do now is opcodes dot return. IL done, guys. We just emitted 2 lines of IL. Very, very simple, right? We now need to go bundle this into a delegate. While we have a dynamic method, we can't call it yet. We have to go create a delegate from it so that it can get JITted, and then we can go execute it like any normal delegate or any normal function, right? So dynamic method has a way to do this very, very simply. Very simple, called create delegate. Ooh. And for this, we pass in our type of funct, right? So we want to create this delegate around, this is our signature, right? And it's just a function that returns our type. It's just a function that returns our type. And then we can use as, and then because it normally returns an object or returns just a basic delegate, we want to then cast it to what we're looking for. Object creator equals, let me see what I did wrong here real quick. Type of, that's not right. There we go, right? So we're going to go create a delegate, and a delegate just returns a delegate, but we also give it the type so it knows what kind of delegate to create. Then we can cast it. We just use as, right? This is just a cast operator into a function of t. And now we have this object creator. And then after this, we spent all that time just initializing our object creator if it's null. So now it's not going to be null. And since this is static, it's only going to be null, not null one time. We can easily, simply execute this. And this will execute our IL every time this happens, right? Let's compile this and see what happens. Things look like it compiled, guys. I'm going to enable chat. And let's see what's going on in chat. Let's talk about this. And we're going to go execute this, and we're going to go see what the performance looks like. All right, guys. Anybody not following what I'm doing so far? Diego, is this usable in normal application? Absolutely. This has nothing to do with game techniques, buddy. This has nothing to do with game techniques. This is just around object initialization. If you have any software where you are creating a lot of objects, for a majority of your time, this will help you. So the IL here, I want to go back to why we created this as a static class for a generic type, guys. The cool thing about .NET and C#, when you create a static class for a dynamic type, for a generic type, every type that you use in your software, wherever you use this static class of a type for the generic, you will get a new, unique, static version of a fast object allocator for this type. So since every type will have its own instance, one instance, right? That means every object will have its own one instance of an M object creator for this type, which means we'll have one object creator delegate baked behind this dynamic IL for every type of T that you use in your code. So funct T is making a function of type T. Funct T, guys, if you don't know funct T, this is just a wraparound delegates, right? This is the same way if you're going to write out an event that says return type T, here's my delegate name, takes 0 arguments, right? So hopefully people are understanding what I'm doing here. The question is it going to pay off? Memory alignment possible in C#? Yes, we're going to talk about that in a little bit, buddy. How is IL? It's right here, my friend. So from the dynamic method, right, we create a new dynamic method from a return type with parameters. This gives us a new method template. There's no IL in here. We get the IL generator off that dynamic method, and from there we can emit IL into it. Hopefully that's clear. Okay, guys, let's go run this. I'm curious. I'm so curious what this is going to do, right? So let's go add on to our little tester here. So this is, we'll call this create IL. This is our IL creation method, right? So instead of calling create reflect, we don't need the type anymore. We're going to use our new function fast object allocator of T, which is object dot new. That's all we want to call, right? So of a fast object allocator for this type. So when I give it a type, C# at the runtime is going to go give me a new, unique, static instance of this class in memory. It's going to be rooted in memory. And then if I gave this a different type, you know, if we say this of string, this is a bad example using string here, but and it won't even work. This will be a separate fast object allocator instance, static, right? So that means our IL, or our delegate, our function delegate, will be unique for the type. Here we go, guys. Let's run this. Let's see if it is any better. Let's go find out. Holy smokes, everybody. Holy cow. What did we have? Half a millisecond for our native. Our generic, our slowest, you think it wouldn't even be the slowest, you think it would be near as fast, is 10 milliseconds. We were able to shave that down to 7.6 milliseconds, right, by using the reflective way. Our IL generator has slammed that down to just having a 1 millisecond overhead, right? So by allowing us to continue to use generics or to continue to dynamically pass in the type, we can instantiate new objects with just a 1 millisecond overhead. Let's see if maybe we can get this even a little faster, right? I don't think we're really going to get this faster, but I want to go try. I don't know, Pyro. Let's go take a look, guys. We got this super duper fast, but maybe we can go even faster, right? So we're going to call a public static fast object allocator And we're just going to bake all of this in up here. Not allowed. Okay, that's right. There we go. Now we move this into our static constructor. This only gets called once, and it's guaranteed to be called before new will get called, right? Guaranteed that our constructor will be called before new gets called. So now we don't have to do any type of branch testing. This is guaranteed to be there. We're going to be able to call this. Let's see what happens. Let's see if it works, or if I maybe broke. Uh-oh. Let's open this back up. Let's see what we get, guys. Let's see what we get. So, as I thought, as I figured, we're not really saving anything in there, right? Because if you think about it, a branch test and a jump in the IL, very optimized. It's not that's not a 1 millisecond type of operation. If it was, C# code would never run on a computer, right? So we're not really saving anything in our software by doing that. But it does make it cleaner. It does make it cleaner. There's no reason not to do it. So we should do it, even though it's not really giving us any type of performance boost. But the great thing is, we still only have about a 1 millisecond overhead. Let's take a look at the IL for this, because always go back to the IL, guys, right? Let's always go back to the IL. Let's take a look. Here's our fast object allocator. Here is our function, which takes a generic, right? What is going on in here? And this is why it's a little slower. I'm going to talk about why it's slower here in a second. We are, instead of just doing two ops, instead of doing two operations, where it's just a new object and then a return, instead we're loading a field, right? We have to load our field into the stack so that we can then call a virtual function, and that's how funcs work, right? It's just going to call a invoke on it, on our delegate. So already that's two calls, that's two operations, and if we remember what's the IL behind this virtual call, behind this funct, is another two calls, right? Because it's the new object and a return, and then we have the return here. So we're talking about 5 ops, 5 IL ops versus 2. And not just 5 IL ops, a call vert is more expensive than a normal call. We'll talk about that. So 5 IL operations, with one of these being a virtual call, versus 2 IL operations of no calls, right? Just new object is a built-in optimized op, right? So that's why we see half a millisecond versus 1.5 milliseconds, right? Makes sense. If 2 ops are half a millisecond, 2, 1, right, almost get back to 1.5, and that virtual bumps it up to round it out. And this will hold true no matter how many reputations we go. If we go a million reps, everything still holds basically true, right? Obviously, the more reps we do, the more likely garbage collection is going to be kicking in on us and starting to poison our results. Because since we are newing objects, we are allocating new objects, and then we're dereferencing those, garbage collection is going to be kicking in on us and starting to be a problem as we scale this up. But there we go, guys. Here is one way you can write a factory object allocator that's near as fast as native. And I know, I'm sure people have already written object allocators out there for and thought they were just as fast because generics, and hey, it's generic, everything is great. Unfortunately, guys, the easy way is the slowest way.